Okay. Hello, everyone. Welcome to another session of online Causal Infeance seminar. Today, we are excited to have Davide Viviano from Harvard University talking to us about program evaluation with remotely sensed outcomes. We are also excited to have Hyunseung Kang from University of Wisconsin-Madison as a discussant. Today's Q&A will be handled by Ying, so I'll pass it to her.
Thank you, Razi. So as usual, please submit your questions in the Q&A section for us to track the questions more easily. And it's you can use the button at the bottom of the Zoom window. Today we have the collaborators of the speaker, Rahul, to answer questions during the talk, and we will raise some questions when the speaker stops for questions. And finally, we encourage you to submit your questions as soon as you have them, instead of waiting for the speaker to ask for questions. So without further ado, please feel free to take over, David.
Thank you very much. I'm going to share my slides. Can you all see the slides?
Yeah.
All right. Thanks very much, the organizer. Thanks for the discussant and for all of you to be here. Today, I'm going to discuss about program evaluation with remote sense variable. This is joint work with Ashish Rambachan at MIT and Rahul Singh at Harvard. And the paper is available online at the following link. So let me start from a very basic observation that there is a growing availability of experiments in social science and in industry. But despite this growing availability of experiments, the analysis of such experiment is often challenging for many reasons. And one of these reasons is the limited access to outcomes that we really care about. So for example, if we want to evaluate an anti-poverty program, typically what we have to collect is data about consumption or other economic variables that are very difficult to collect in practice. To collect consumption, we will need to go to people and then ask to people what they consume in the past month. Similarly, if we want to evaluate programs such as anti-deforestation programs, what we will need to do is to measure the extent to which there are forests in different plots of land to be able to understand whether certain programs had an effect or not. Now, motivated by this observation, the recent literature has complemented traditional analysis with what's known as remotely sensed variables. And we can think of them as night lights, satellite images, mobile phone data, noisy surveys, or any other of these type of variables. And one big pros of using this type of data is that it's typically very cheap to collect. So this data can be easily downloaded online, such as satellite images, and it's also high dimensional, and so it may carry lots of information about what you truly care about. Now, the problem is that exactly because it's high dimensional, it's also quite noisy with respect to the outcome of interest that we want to understand, and can be hard to analyze. And so this raises the question of how and also when we should use this type of data for program evaluation. So let me give you some motivation behind the problem. So this is a working paper, and more broadly is a platform which has been launched by people at the World Bank, where what they do is that they collect information about villages in India. So for each village in India, they have latitude and longitude data, and then they provide night lights, which can be accessed online directly. Now, using this data, we may think to analyze certain experiments that we may run across these villages, for instance, to see what's the effect of anti-poverty programs or other type of programs. Now, a different example come from environmental economics. In this paper published in Science, the authors, what they do is that they provide cash to the people to reduce land that farmers use, and so to reduce deforestation. Now, it's very hard to measure deforestation, and so what the authors do is that they're gonna look at different images, and for a small subset of image, they're gonna label whether you have a forest or you don't have a forest, and then they're gonna try to predict treatment effect by using satellite images in the experiment and predict whether there are or there are not forests across the treated and the control farmers. Now, another successful story of using this type of data is to evaluate cash transfer programs. So these are programs where researchers provide cash to poor individuals, to study the effect on GDP growth. And again, they do so in this example using satellite images. Now, together with this successful example, there are also less successful examples where this type of data does not work as well. So in this paper, the authors, what they study is the effect of a COVID relief program, and they observed that by only using remote sense variable, in particular mobile phone trace data, they are not able to recover treatment effect that otherwise they would be able to recover by just looking at the outcomes directly collected through survey. And so this raises the question of whether this is an issue of the econometric technique that they use, this is an issue of the data, or both. So let me give you this paper just in one slide, and then I'm going to expand on the details of the paper. The setup that we consider is the following. We have two sets of data that we're going to define as an observational data set and an experimental data set. Now, in the observational data set, what we observe is the outcome that we truly care about, say consumption data, and also the remote sense variable, such as, for instance, satellite images. Now, in the experiment, what we observe is a treatment which has been randomized, say, across different villages or across different individuals, as well as satellite images, or more broadly, a remote sense variable. But we're not able to observe outcome because, for instance, collecting consumption data may be very difficult to do for the researcher in the experiment. So what we're going to focus on is a setting where the remote sense variable denotes a post-outcome variable. So we can think that, for instance, if we treat individuals by providing cash transfer, this may affect consumption, which then may change luminosity that you observe through images. And what we're going to provide is a principal way for inference on treatment effects on the outcome that we care about in the experiment by following four main steps. So as a first step, we are going to ask the question of whether we can evaluate treatment effect by just training a predictor on the observational data set that try to predict the outcome using the remote sense variable, and then compare this prediction between the treated and the control units in the experiment. Now, in a counterintuitive way, actually it turns out that this approach has a bias, and so does not return consistent treatment effect estimates. So we then provide identification argument, which is a constructive identification argument, to be able to identify treatment effect from this setup, and show after that how we can use arbitrary algorithm, machine learning algorithm, to compress these remote sense variables, such as a satellite image, in an efficient way to then estimate treatment effects. Now, what's important that in the framework that we provide, we are not going to impose assumption on how our outcome of interest may affect downstream the remote sense variable, such as, for instance, how consumption may affect luminosity in each pixel of the satellite image. And instead, we're going to argue that we can obtain consistent estimate even when we don't know this relationship. And finally, we illustrate our method by studying a large-scale public policy program which was implemented in India, and by showing that we can recover point estimates with higher level of precision, even by using less information in terms of the outcome of interest, by augmenting the dataset through satellite images. Now, I cannot give justice to all the literature, so let me just briefly mention some of the main references. So of course, there is a growing econometric literature which studies problem of data fusion. And we think of data fusion as a setting where we have different data sets that we would like to combine for different reasons. So for instance, there is a literature which studies how we can run long and short regression, which consists of running regression where we have data sets which contain different covariates, but we would like to control for, say, all of them. Now, our problem is different because the problem is not that we don't observe the covariates, but rather we miss the outcome in the experiment. Now, there is a literature on surrogates that connect more closely, where what the author have are two data sets. In one data set, they observe a treatment and a short-term outcome, and in the other data set, they observe a short-term outcome and a long-term outcome. And the final goal is to conduct inference on the long-term outcome. Now, our problem is different from the surrogate because our goal in this same setup is not to conduct inference in what they define as the long-term outcome, but rather as to conduct inference on the short-term outcome, which is not observed in our setting in the experiment. And so none of these study a missing data problem where the outcome of interest is missing and where the auxiliary data set has a post-outcome variable. Now, a different way to approach this problem is by actually posing a generative model on how the satellite image may change as a function of the outcome of interest. For instance, we may say how each pixel of the image change as we change consumption, or if we have text data, how text data may change as a function of some outcome that we care about. Now, the main difference from this literature is that here we don't want to specify the relationship between the outcome and the remote sense variable. For instance, it seems difficult to specify how each pixel may change as a function of consumption, and so we want to be agnostic in that term. Finally, more broadly, we connect to a literature measurement error and machine learning imputation, and the main distinction here is that this literature mostly focuses on missing covariates, or in setting where the outcomes is observed or partially observed in the main study of interest, which is not the case in our setting. So let me briefly discuss the main setup. We have some treatment, which is binary, and I'm going to denote with letter D. So either is 0 or is 1. We have some potential outcome, y of 1 and y of 0, so I'm ruling out any interference. So I'm going to assume that I only depend on my own treatment, and the outcome we observe is either the potential outcome under treatment if I'm actually treated, or the potential outcome under control if I'm not treated. Now, I mentioned to you that we have two different data sets, and so let me denote that with this letter S. So if S equal to E means that we are in the experiment. If S is equal to O, it means that we are in the observational study. And now let me denote with the letter R the remote sense variable, such as a satellite image. Now, what do we observe? So we're going to observe n units, and for each of these n units, we're going to observe whether the unit is treated or not, which is denoted with D, the satellite image, which is denoted with R, whether the unit is in the experiment or in the observational study, which is denoted with S, and then we are only going to observe the outcome for those units in this observational dataset, but not for those in the experiment. Now, of course, you can think of some extensions. For instance, you may think of having some covariates. For instance, we may think of setting where we observe some outcomes also in the experiment. These are discussed in the paper, but I'm going to omit those through the presentation. So the model that we have in mind goes as follows. We may be in an experiment or in the observational study. Now, if we are in the experiment, for instance, the treatment may be randomized, so some units may be exposed to treatment. And so this may affect D. Now, my treatment may also affect my outcome. And now, the observational study may have some treatment, may not have any treated unit. There may be some confounding, so we're not going to impose assumption in that term. Now, what's important then is that we don't directly observe the outcome in the experiment, but we observe the satellite image. And we think that the outcome may affect the satellite image, so may affect what we observe from the image. And maybe there might be also some direct effect from the treatment to the satellite image. Maybe there are not. The key assumption that we're going to impose is a form of stability restriction. So we're going to assume, in some sense, that the relationship between the outcome and the remote sense variable, say the satellite image, is stable, is the same between the experiment and the observational study. Now, given this restriction, our goal is to conduct inference on the treatment effect in the experiment, the average treatment effect. Now, individuals in the experiment or observational study may have different D. Individuals in the observational study may not even have any treatment. And the key assumption is this stability restriction, for which this relationship remains stable between the outcome and the remote sense variable. So let me try to formalize a little bit more the condition. The first condition is standard. We just have an experiment. So the treatment is randomized, is independent of my potential outcome, conditional on me being in the experiment. And I have some overlap, so some treated unit and some control unit in the experiment. Now let me discuss condition 2, which is about this observational dataset. Now the first condition is that the outcome has a common support between the experiment and the observational dataset, and this is intuitive. If it doesn't, then we will need to rely on some extrapolation method. Now the second condition is that either some units receive cache transfer, so have some treatment in the observational dataset. The treatment does not need to be randomized, but some units are exposed to treatment, or if that's not the case, then there are no direct effect of the treatment on the remote sense variable once I control for the outcome. Now, this is intuitive. If I have no observation whatsoever about units who receive cache transfer on their outcomes, then I'm not able to identify treatment effect at all. And so I will need to remove to assume that there are no direct effects. So the third key condition is the stability restriction. So whether I am in the experiment or the observational study does not matter in terms of the relationship between my outcome and the remote sense variable. So just a few points to keep in mind. The first is that these conditions are jointly testable, and I'm going to show you later how we can do that. And the second one is that if we expect some direct effect between the treatment and the satellite image, for instance, cache transfer may not only affect consumption, but may also affect employment, and we don't observe employment. And so through employment, the satellite image and the night lights may change, then we will need to collect some outcomes which are exposed to the treatment in our experiment. And so this may guide the way we also survey individuals in the experiment. Okay, so given this setup, we would like an estimator with the following desiderata. So the first, we would like an estimator which has an infinite variance if our satellite image is independent of consumption. Now, this makes sense because if I'm not able to predict consumption using satellite image and I don't observe consumption in my experiment, then I will not be able to make any inference on treatment effect at all. Now, the second one, however, is that if there is some relationship between the satellite image and consumption, we would like a consistent estimator. And also, we would like something that does not require how consumption may affect what we observe in the satellites. Now, that will be a bonus, but ideally, we would also like to have an estimator which is efficient, in terms that is able to compress the satellite image in an efficient way once we do inference on treatment effect. Okay, so let me start from a first observation. And the very first thing I will do personally will be the following. Once I look at this problem, I will say, okay, let me just estimate from my observational dataset the expected value of my outcome conditional on my satellite image. And let me create this conditional expectation that I'm going to denote with this as function. Now, let me just go back to my experiment and let me compare the treated unit once I plug in my predicted value for the outcome for the treated, and the control units once I plug in my predicted outcome for the control unit, which is captured by these two components. So I'm going to just look at the difference in the predicted outcome between these two groups. Now, of course, we may think that this estimator will converge to something, and so the question is, what is this something? Now, this something is going to be the expected value of my prediction, conditional on me being treated, minus the expected value of my prediction for the outcome, conditional on me being under control. And so this type of exercise, what it's doing is that it's replacing this remote sense variable with a surrogate model. So it's saying, okay, let's just think about this as the following problem. We predict the outcome using the remote sense variable, and so we get a prediction from this first component, from the observational dataset, and then we plug in this prediction to estimate treatment effect. Now, what we have just been doing is to replace the role of y, which was here in the middle, with the role of r, which was here. So it flips the two. And so the first question is, okay, is this a sensible approach to do? Well, the initial intuition would be, well, maybe yes, right? Because my prediction just take an expected value, and so we can think of predicting the outcome just as having a noisy measurement of the true underlying outcome. So we could write our f of our function, our expectation, just as the outcome plus some noise eta. So maybe that's fine because the noise just is added to the outcome. But I'm gonna argue that that's not the case in a very simple example. So suppose that we have just a univariate variable r. This is just living in R, so it's a very simple variable. Let me assume that I have a very simple linear model of R as a function of y, plus some noise. Let me assume also that theta denotes the treatment effect, and so I remove intercept for simplicity, and I also have some noise here. Now, what we have been doing here is to say, okay, let's create a conditional expectation of y given R through a linear regression. And so this is gonna be equal to R times a coefficient beta star. What is beta star? Well, beta star is just the covariance of y and R divided by the variance of R. So let's look back at the probability limit of what we were estimating before by using this surrogate method. So we can write this probability limit just as our beta star, which pops up here, times the expectation of R given that I'm treated minus the expectation of R given that I am under control. So now let's replace the expression for R with the expression that we have here. So again, we have beta star times y times beta minus expectation y times beta if I am treated or I am under control. Now let's replace the expression for y using the expression again here. So again, we have beta star d theta beta minus d theta beta if I'm treated or control. And so this becomes just beta star times beta times theta. When is theta tilde, this probability limit of this exercise, equal to theta? Well, it's equal to theta when beta star times beta equal to 1. But what is beta star times beta? Well, this is just the covariance square of y and R divided by the product of the variances. So this is just the square correlation coefficient. So what's happening in this type of exercise? Well, the true model is a model where D goes from Y, which goes to R, and each arrow is characterized by a given treatment effect, theta and then beta. But we are replacing the role of R and Y in this regression approach. And so we're getting something which also depends on the relationship between Y and R, exactly through this correlation coefficient. So what is the implication? Well, the implication is that if there is no relationship whatsoever between the outcome and the remote sense variable, so if this beta equal to 0, we're gonna get a precise estimate for the treatment effect, which is exactly 0. But this is the opposite of what we would like to get. If there is no relationship, then we should not be able to make any causal claim about treatment effects. And so this is just an informal theorem which shows that there's gonna be a bias. Typically, this may be an attenuation bias when we do this inverse regression approach. So let me stop here and take questions.
Hi, David. We don't have active questions for now, but we encourage the speaker, the audience to submit questions as soon as you have them. Thank you for asking.
Thank you. Okay, so let me proceed then. Okay, how can we proceed with identifying treatment effect now? Well, to keep things simple, let me suppose that the outcome is just binary, so either is 0 or is 1, and there is no direct effect, so that there is that this treatment is independent of my remote sense variable, conditional on my outcome. So again, this is not necessary for our argument, but it's going to simplify exposition. So the first step for identification is going to be to look at what we can observe from the experiment. So what we can observe from the experiment is the distribution of our remote sense variable conditional on being or receiving a certain treatment D and being in the experiment. Now, how can we write this distribution? Well, we can sum over the value of our outcome, which can take either value 0 or value 1. And now we're gonna get a conditional distribution of the remote sense variable conditional on the outcome. And will multiply the distribution of our potential outcome taking a certain value in the experiment. Now, what we really care about is this object here, this probability. But there's going to be some weights, and these weights are scary because they do depend on the conditional distribution of R given Y, but we don't really observe Y in the experiment. So now we're going to use the stability assumption and also the restriction that there are no direct effects, so that we can write these weights, this conditional probability, just as the probability that R take a certain value given Y and given that we are in this observational dataset. Now, this object now is identified, but still is quite a complex object because R can be high dimensional. So the probability of what we observe in the experiment is going to be a mixture of such probabilities. So the second step is going to be to take differences between the treated and the control unit. So let's go back to what we can identify from the experiment, and let's look at the treated unit and compare them to the control units. Now, from the argument before, this difference is going to be equal to our treatment effect data that we really care about, times a difference between this conditional probability of R equal to R given that Y is equal to 1 and I am in the observational study, and R equal to R given Y equal to 0, so this is a typo, I apologize, given that I am in the observational study. And now this difference is going to define how the remote sense variable changes if we change the outcome. So this is the beta in the previous expression. Again, this is a type with Y equal to 0. So what we are observing is that if we look at this overall effect, this is going to basically be given by the product of this theta and this beta component. Now, the main issue here is that these probabilities are hard to predict because R can be a complex object. So what can we do next? Well, we can just use Bayes' rule. And so we're going to write the probability of R given me being treated and being in the experiment just as a ratio of a probability that I receive the treatment and I am in the experiment given R divided by the unconditional probability times the unconditional probability of R. Now, this first component, this very first component, is a very nice component. It only depends on these indicators, or whether I'm treated and I am in the experiment. But the second component is complex because it depends on the the probability of these pixels, for instance. So what can we do? Well, let's go back to our differences. We were using differences before. We use differences for this component, but we plug in what we just obtained. And so what we're going to get is that the difference between this ratio of probabilities multiplied by this scary object is going to again be equal to the treatment effect we care about. And now again, we're going to have the same expression for the outcomes as we have for the treatment, which multiply again for this same scary object. And so what we can do now is that we can simplify the expression with respect to this unconditional probability and obtain an expression which does not depend on the distribution of the satellite images. So what this implies is that we can identify treatment effect without having to require and to specify a model for how the satellite image change. Everything only depends on this conditional probability of treatment and outcomes conditional on the satellite image. Okay, so but how do we proceed in practice? What does that mean? Well, this means the following. We can just take a difference between indicators function. So we're going to look at one indicator, which is the indicator of me receiving treatment and me being in the experiment, minus the indicator of me being under control and me being in the experiment, divided by this unconditional probability. So this is something very simple to obtain. And we construct these same indicators for the outcomes. And now what we just observe is that our treatment effect is identified through this set of conditional moments, where the expected value of this difference in indicators for the treatment minus our treatment effect times this difference in indicator for the outcomes given the satellite image equal to 0. So now this expression is going to be true for any value of the satellite image. And so we can take even any summary of the satellite image, and it's also going to be true. We can use the average luminosity, the maximum luminosity across pixel, and all of these are going to satisfy these restrictions. So the implication is the following. We can take any function of R, let's call it this h of R, for instance, just the average luminosity we observe in the satellite image. And let's suppose that this representation is sufficiently correlated with the outcome, with how the outcome changed. So there must be some correlation with the outcome, otherwise it will not be predictive of the outcome. And our treatment effect is just going to be given by a ratio of expectations. On the numerator, we have something which defines how the treatment changed and how it correlates with the summary of the satellite image. On the denominator, we have this correlation between how the outcome changed times this same summary of the satellite image. So we just look at variation in treatment and rescale it by the variation in the outcome. So the intuition is the following. We see how much R and D co-move together. We note that some of this co-movement should be attributed to how Y and R co-move together. And so we are properly divided by how much Y and R co-move together to be able to recover the true treatment effect. Now, what's very nice about this result is that it also provides us with a testable implication for our model assumption. In particular, from this equation, we do observe that theta is not a function of h of R. So if we take the average luminosity, if we take the maximum luminosity or something else, we should always get the same estimate for treatment effect. And so we can use this as a testable restriction. If we start changing h of R and we do observe different results, well, that means that probably our model, so the stability restriction, fails. And so this provides us with testable restriction for our assumptions. Okay, so that seems interesting, but in principle, so how do we pick h of R? Like, is this the average luminosity? Is this something else, weighted luminosity, just a prediction of Y given R? How do we pick h of R? So how do we optimally summarize satellites into a single component? And the intuition goes as follows. Going back to our model we had before, we can write this change in treatment just as a linear function of the change in outcome plus some error term, which is conditional mean independent of this remote sense variable. So as mean 0 given R. So this seems just like an instrumental variable problem. And just like an instrumental variable problem, we also know what's the optimal h of R, the optimal instrument, quote unquote, in our regression. And so the optimal instrument is just going to be the predicted value of the change in outcome given the satellite image once we appropriately adjust by heteroscedasticity, so by the variance of this residual epsilon. Now, given this expression, what we can try to do is to try to predict this expectation and this variance, and then just plug it in and use this predicted value for our representation of R. What this means? Well, it means that we're going to look at our data set and we're going to train a machine learning model to predict Y equal to 1 given R in the observational data set, to predict the treatment in the experimental data set, and also to predict whether I am in the observational on the experimental data set. Now we're going to aggregate all of this prediction using the formula just provided before. Of course, this is a particular formula. We can just aggregate them. All depends on this prediction we estimate. And we come up with this H hat of R, so this efficient representation. Now, given this H hat of R, we can just estimate our treatment effect by looking at the correlation between the change in treatment and our representation, and the correlation between the change in outcome and our representation. Now, what's powerful about this approach is that as long as this function converges to something, it doesn't need to be correctly specified, it doesn't need to converge to something specific, as long as a probability limit, we can just use standard inference through the delta method for inference on theta A. And this follows similarly to the literature on conditional moment equalities, dating back to Chamberlain 1987. So if you want to use a machine learning techniques, you can just do that as long as you get enough correlation between your representation and the change in outcome. Okay, so just to put things in perspective, how does the method works in practice? Well, the first step is just to choose your target. What is the outcome that you truly care about? Make sure that this outcome is simple, and these are the assumption we make in this paper. For example, is binary or discrete. Then step 2 is going to be to train your machine learning model. So train your machine learning model on the observational dataset to predict the outcome, on the experimental dataset to predict the treatment, and then aggregate this prediction to form your optimal representation. Now, there are some warning signs that you want to listen to. So the first is whether your predicted value, your representation, does not correlate with the change in outcome. Now, if your representation does not correlate with the change in outcome, you are in a world of a weak instrument problem, in the sense that the variance of your estimated effect may be infinity just because you don't have enough information from your data. And so this is going to be the first warning sign. The second warning sign is that the moment you start changing the way you construct HOR, results should be more or less similar. And so this should give you a sense of stability restriction and robustness of your results. Now, if you also expect direct effects, please collect some outcomes from the units that receive some treatment. For instance, some units who receive some cache transfer. Now, step 4 is going to be estimation and inference, and here we can follow just standard methods of moments. So let me stop here in case there are questions.
Hi, David. There are 2 active questions regarding the assumptions you take. Maybe we read the first one. So concerning your DAC, for many applications, the relationship between the Y and the RSV is not that clear. It might even go both ways. For example, predicting consumption expenditures from satellite images. So consumption expenditures might affect luminosity, but for example, the state of vegetation also influences consumption expenditures, in particular in agriculture-based economics. Do you have any thoughts on how this would affect treatment estimates?
Okay, so I think there are 2 answers to this. The first question is, what if there is a reverse causality issue, in the sense that my consumption may affect satellite image, but then satellite image effect itself may affect my consumption. And so in this case, we cannot say much because we don't have a direct cyclical graph. That is, the relationship is just a relationship where you have reverse causality. So there's no much to do unless you are able to pin down the correct direction of causality. Now, we believe that in the setting that we study, this is quite unlikely, in the sense that it's hard to think of a setting where the change in satellite image themselves may go back and change consumption. And especially in many of these settings, you have a panel. And so you can also use the time dimension to be able to regulate what affects what over time. Now, the second question is about, the second issue may arise if there are direct effects. So maybe consumption affects satellite image, but maybe also something else affects satellite image, such as employment. But you don't observe employment. And the treatment may also affect employment. Now, what happens in this case? But if there are direct effects, then what we argue in the paper is that you can still achieve similar identification argument, but you will need to observe some outcomes which are exposed to treatment, either in your experiment or in your observational study. The treatment does not need to be randomized, but you need to observe some outcomes there. Otherwise, you need some bounding exercise because there's no much you can say. So these are the 2 answers.
Thank you so much. Another question, which might be a bit related, is could you describe how the comparison might apply if R is something more complicated than luminosity? So for example, in environmental applications, R might be a constructive variable based on machine learning type processes that translate satellite image to a descriptive measure such as forest, deforestation, pasture productivity.
So these are great questions. Yeah.
Yeah, please go ahead.
So this is a great question. Thanks for asking. We think that the power of the machinery that that we built here is exactly the fact that it does not require assumption of what this R is. So R may be satellite image directly, so it may just be the raw data. R may be the prediction of first obtained from a machine learning model. It may be some other summary that you obtain. We're not making assumption about that. So whatever R is given to you, you can use that R. It may be multivariate, it may be univariate, it may be a summary of these things, it may be first obtained through a machine learning technique. All of them are completely fine. And in fact, it's just a redefinition of what is R. And the reason is because the set of the identification that we provide holds conditional on any such R. And so it can also be just a summary of this R, such as just a prediction of the land use through already using a machine learning model. Now, what is important, however, is that the summary that you obtain, for instance, the prediction through the machine learning model, in some sense are predictive of the outcome, because otherwise you're not going to be able to draw any inference because they're not informative of what you truly care about. But we think this is a reasonable restriction, because otherwise these are just uninformative about the question you care about.
Thank you so much for the answer. That's all of our active ones, and I think Rico have been answering some other questions, so we can
Thank you.
move.
Okay, let me briefly conclude through the empirical application. So the experimental background is where we want to use remote sense variable to evaluate anti-poverty program, and we focus on the smart card experiment. This is an experiment that consisted of deliver payment securely to beneficiary. These beneficiaries are typically people, very poor individuals, was implemented in India and involved millions of individuals. The experiment by the original authors was shown to be very effective in increasing consumption and GDP growth, and consistent of randomizing treatment across some control mandals, this is the equivalent of a county in the US, and some treated mandals. So we have about, in total, 170 control units across two different groups, and about 110 treated units. And finally, there are also other counties which are not in the experiment but collected by the authors, and these are about 100 of them. So what we're going to do is that we're going to use village level information as well as satellite image to estimate the treatment effect. And we're going to compare the point estimates between different exercises where we're going to fake a setting where we have no outcome variable, we only have limited access to the outcomes, and see what happens there. So this
Sorry,
is
David, to interrupt.
Please.
Just to remind you, you have like at most 5 more minutes so that we have time for the discussion as well. Thank you.
Thank you. So this is the map of the experiment where we have some control units, some treated units, some buffer units, and this is how we collect data. So this is an example of a village. We obtain the satellite image from the village, and we draw the boundaries, and then from these boundaries we can just compress this image through a set of 4,000 variables which obtain through mosaics, which is a particular method to compress this type of images. And here I'm just plotting the first principal component that we obtain from this 4,000 vector. So the first exercise is going to be to try to predict consumption data that we observe from a census, and in particular predict whether individuals consume are below a certain degree of consumption using a machine learning techniques and using the satellite image. And so the outcome of interest is whether per capita average consumption in a given village is below the first quartile. So on the left-hand side, I'm plotting just our prediction obtained through a random forest, where we do observe some negative relationship between whether I predict if I am in a low consumption group and the level of consumption. Now here on the right-hand side, I'm reporting the H of R, so the optimal representation. Now this optimal representation takes a funny shape if we look at that. But then just remember that our outcome in this example is binary, whether consumption is below the first quartile. So what I'm going to plot with this red line is exactly whether we are in a low consumption group. And here what I'm going to plot is whether the optimal representation is 0, so it's positive or negative. And so what the optimal representation is doing is that it's maximizing the correlation that we have between that and the outcome to be able to be efficient in how we summarize our data. So we're going to look at 3 metrics. whether consumption is before its first quartile, whether no individual in the village has an income above 5,000 rupees or an income above 10,000 rupees. These are metrics of poverty. And we're going to look at two validation exercises, where first we use the outcome for the first half of the experimental mandals only, and not for anybody else. So only you use information from half of the outcomes that are actually collected. And the second one is where we use the outcomes only for the buffer control group and the holdout sample only. And this is again half of the sample, half of the outcome that we truly have. And we're going to compare our method to a regression that uses the outcome for all the information, for all the villages that we have in the experiment. So this is the comparison that we have. The true regression is going to report a point estimate, which is about here, quite close to our regression, which are the red and the green using different type of data set. But more interestingly, the true regression is also slightly larger confidence interval, despite using twice as many the outcomes that we use. And the reason is because here we are augmenting our regression also with the satellite image, so to improve precision. And so despite observing only half of the sample, we are able to even improve precision in this example. Now, there are some simulations in the paper that I'm going to skip, and let me just briefly go through a few of the extension where we discuss the case where the outcomes may not be non-binary. And so in this case, identification is more complex and is going to require some rank restriction between how much the satellite image covariates with change in outcomes at different values. So as the outcome has more and more support point, identification becomes more challenging. We also have extension where the outcomes, some of the outcomes are observed in the experiment and where there are direct effects. So to conclude, in this paper, we study program evaluation with a most sense variable. We review some pitfalls for practice and provide a constructive identification argument. We require no model specification on how this remote sense variable relates to the outcome and can use arbitrary machine learning algorithm. And then we reevaluate a large-scale public policy program. So there are many open questions for future, spillover effect, high-dimensional outcome, noisy measurement that we leave for future research. That's pretty much it. Thank you very much.
Thank you, David, for the very interesting talk. There are no questions at the moment, no more questions. So maybe I can pass the floor to Hyunseung for his discussion. Hyunseung, you want to share your slides?
Sure. Give me one. Once David's, yes, great. So thank you for the wonderful talk, and also thank you for the organizers for organizing this as well, and the invitation to give a discussion on this very interesting paper that I read. So I'll go through it quickly just so that we have more time for the discussion afterwards. So let me just start by just summarizing how I interpreted this paper and how I saw the setup of this paper. This is, again, thanks to David's wonderful presentation, the paper that's already. So roughly speaking, you have two data sets, the experimental data set and the observational, or really a survey data set. An experimental data set, let's say you randomize treatment, but you don't get to observe the primary outcome that you're interested. You instead observe what they call remotely sensed variable R. In the observational study or survey data, I'm going to focus on the case where there's no control, and everyone's control, and then you get to observe all these three things at the end of the day. And so the goal is to estimate this little point here, the effect of the treatment and the primary outcome, but none of the primary outcome is observed, and that's the biggest challenge. And also, you can't necessarily directly borrow information from the observational data because it's confounded. The treatment is confounded there. And finally, this R is a post-treatment variable, which is that it's affected by the treatment assignment. So the idea, the problem that they tackle is how do you estimate the treatment effect in this particular setup where none of the primary outcomes are observed, but you have this auxiliary data where it's confounded, but maybe you can borrow some information from there. So I think there are two, in my opinion, key assumptions that enable this approach. The first one, they call it RSV stability. It's essentially just a version of exchangeability, transportability. Effectively, it just says that the R variable, the RSV variable is exchangeable with respect to whether you're in the experimental sample, observational sample. You can borrow information across, essentially, is what this assumption is saying. And this one, there's two variations of this assumption, 3.1 and 3.2. The second one says that once you know your primary outcome, that there is no direct effect of treatment on the outcome. That is essentially one version of the two assumptions that they make. in the paper as well. So given this, then you can kind of, and in addition to this, I actually thought what the presentation did was actually a model that really helped me clarify what's going on and the problems that I have is this very simple linear model that he actually also described in the talk, which is essentially you have this data generating process, you have the outcome of interest, and then there's a treatment, and you also have this response RSV variable that's also related to Y. And the goal is to essentially identify and estimate this, but you're only given not every possible variable Y, R, D, but you're only given R and D from the RCT data, and you're only given R and Y, the second part, in the observational data. Now, if you think about this model for a second, if I give this to an undergrad student to ask how do you estimate this thing, what the paper describes as a common approach seems very silly to do. You would never ever run a regression of Y on Y to do this, because if the data generating model looks like this, then this would violate what we would teach at an undergrad level how this regression is done. And therefore, anything that comes out of this to get estimate of this seems silly. And I appreciate actually what their summary of the first result is. They actually made this more formal and justified in many ways. They not only said this there's a biased attenuation, but the sign can flip. And they talk about how you can identify this treatment effect at the end. I think one of the most useful expression that is conceptually helpful to me is this ratio, or they call it the inverse IV estimate. And essentially, it's a change in some the variables in the experimental sample divided by some change into some variables in the observational sample, reweighed by the RSV variable at the end of the day. And to me, the way I see this paper is I see it as one of a broader contribution to extend results in nonlinear measurement models, attenuation bias, identification, all these other things by data fusion. I haven't seen much of this in at least my exposure to measurement error models. Most of the time it's dealing with distributional assumptions, or you have repeated measurements to try to obtain unbiased estimates of the measurement, the true value you're interested. It's an interesting area that could probably go in further research down the road using data fusion to mitigate some measurement error problems at the end. And in this particular case, they're trying to study the ATE in this, what I'll probably say, somewhat unique measurement error setup. And I guess this is where I would start to have my own commentary on this. So one possible related work, I think, that the authors may or may not, I'm not entirely sure if the authors have considered this, is actually treatment effects with latent variable models. So in political science, educational science, and psychometrics, in fact, there's a whole community, I think, at Harvard that does this. They're looking at the effect of treatment policy on some latent constructs of interest at the end. So for example, the latent constructs we see in math ability, liberal beliefs, openness to immigration, openness to certain policies, and then R is some observable constructs. So like yes or no answers to do you like to have an open border policy or closed border policy at the end. And then D is some treatment variable or policy variable that you're interested in treating at the end of the day. And there are a lot of similarities between this setup and the setup that the authors talk about. The Y is not observed in any of this setup. There is no way to directly observe a liberal belief. R and Ds are always observed, you answer yes and no questions to some political science, comments about your policies, stances, and treatment of observation. And the goal often is indeed, how much does your liberal belief shift after a certain kind of pamphlet thing at the end. Now, there are obviously differences, of course. One of it is that usually in this setup, they only deal with one data set, and thus there is no need to have RSV stability that allows you to borrow information across. And more importantly, the other one is that in this literature, they often use a well-established parametric or semi-parametric models between Y and D, because they have, when they design these constructs and items, they have a very good idea on how to ask certain questions to get really good, precise estimates of liberal beliefs or openness at the end. Whereas in the paper, they take a more non-parametric, or let's let the machine figure out what this project is. There's some key references here I thought could be useful for the paper to potentially benefit from this. This is the most recent paper in the American Journal of Political Science. And there's other ones, and even Naoki also did some work. I actually think this is also very useful because text, they use text as the R variable, and Y is some feature of the text, how positive sounding the text is, how negative sounding the text is. And I thought these could be another interesting application of the author's approach that could be thought about here. Having said that, some questions that I thought would be interesting to discuss. One is, when I looked at this, the first thing I thought about is why not actually study the effect of this on R rather than the effect on the primary outcome. One of the examples that they mentioned in the paper is this deforestation. personally, I was looking, so I worked in agriculture data, and usually we look at percentages of agriculture productivity or where the agriculture productivity happens. And it is of interest to look at the actual direct satellite image and subsets of this satellite image, or even a functional of this thing at the end of the day. So I was curious to hear what the author's thoughts are on this. The other one related to this is one of the problems is because these Y and R is a proxy of Y, and Y is temporal precedes R. And one thing I was thinking about is why not redefine Y so Y is some fixed deterministic function of R. And this happens somewhat frequently in radiology and medical data, where R is some imaging data to see whether you have cancer or not, Y is whether you have lung cancer or not, and D is some treatment for disease. And usually this diagnosis of a disease is a complex but usually deterministic function of R. And this is another way to kind of bypass some of the issues that they described at the end of the day. The other thing is more technical on the setup. I was just curious whether you can allow for an unmeasured confounder between Y and R. This is a problem in surrogate literature. I wasn't sure if the authors have looked into this particular issue. And finally, I'll end this discussion with this. Throughout this, I wasn't entirely sure how unique or special this setup is. So just to give context, like if an investigator wants to run an RCT study AT on a well-defined primary outcome, consumption, labor productivity, but the investigator, instead of measuring that primary outcome, they collect a more complicated object, a satellite image that attempts to proxy this at the end of the day. And it wasn't entirely sure how frequent this setup is or will be in the future. Having said that, though, I do think that the paper provides a very valuable economic contribution to how to deal with estimation of treatment effects in this setup. But I'm just curious to hear both the authors and maybe the entire floor's thoughts on how frequent or common this setup would be now and in the future. Again, I don't have experience with this type of data. And thanks for the wonderful talk again.
Thanks, Hyunseung. David, do you want to share your thoughts?
Yes, thank you very much. Thanks for the wonderful discussion. This is extremely valuable. I agree with everything you said. I really appreciate also the reference you provide in political science. I think that's also an interesting avenue for applications. So there's not much to say. I also agree with the similarity and differences. Definitely the non-parametric approach is a key advantage, especially if we think of summarizing high-dimensional data with respect to literature on latent variable model, as well as the presence of two different data sets different from this literature. Now, let me move to your questions. So the first question is why not to study this difference in the potential outcomes? This is a very interesting question that really depends on the problem at hand. I think the people we have been talking to, and these are mostly people working in development economics primarily, but also in environmental economics, we realize that oftentimes they do care about the underlying outcome of interest, and that also motivates the way they run surveys. So one example is caring about consumption data. A researcher puts lots of effort to collect consumption data, which is often very difficult. And so the question is, okay, how can we put less effort to collect this data? Because ultimately, that's the type of outcome that you care about. And similarly, also investors or founders, they typically look at this type of metrics, which cannot be directly obtained through the satellite image. But of course, that depends on the application at hand. Now, why not to define Y as a fix? This is also a great question. I think for sure there are lots of applications where that's the case, such as imaging data. I think here of the error also has a prediction error. So maybe the R is so high dimensional that indeed it can perfectly predict Y, but the model that we're going to apply to R is going to be a limited class of model, maybe just because of computational restriction or also just for estimation error. And so even in this setting, I think of the error almost like a prediction error that comes out of that. But of course, I agree with you that this is also an interesting class of problems and it's worth to think more about that. Then for the last two questions, so on the unmeasured confounding, so that's something that we rule out. So we cannot allow confounding in the experiment. Of course, if you have instrument or things like that, that's possible, but typically we don't allow confounding in the experiment, so that's required. We can allow some direct effect, but no confounding. And for the last question, how unique or special is this setup? So we do think that this setup actually applies quite broadly, as I mentioned before, both to the context, in the context of environmental economics, but also development economics, and maybe, as you mentioned, also other contexts such as political science and so on, although we have looked less into that. And if we think about environmental economics, we do see lots of application where people use satellite image to evaluate programs. One example was the Cash for Carbon paper that I just mentioned, and similarly in the evaluation of anti-poverty programs. So I think there are a bunch of them, but of course I'm very happy to hear more from you and all the audience. So thank you very much.
Thank you.
Great. So Hyunseung, you don't have anything to respond to? Okay, great.
No, I mean, it's more of an open, and I just really wanted to say, I think the paper is very valuable. I don't mean it to be in a negative tone. I just wanted to, it's just coming from my background in health sciences, it was a very odd kind of a setup to define why post-actively rather than this way. So I just wanted to hear your thoughts on it. But yeah, thank you for, again, a wonderful talk. The method, I think, is very valuable. And yeah, I don't have any further comments to say.
Awesome. All right. Thanks again, everyone. Thanks, David, for the interesting talk, and Hyunseung for the very interesting discussion points, and Rahul and the audience for the Q&A. So let me just wrap up by sharing the information about next week's seminar. So for next week, we will have Anne Helby Peterson from University of Copenhagen talking about two perspectives on interpretable evaluation of causal discovery algorithms. And we will have Vanessa Didolos from the Bremen Institute as a discussant. Hope to see you all next week. Thanks.
Thank you very much.